Welcome back to the deep dive. Today we are, well, we're not just looking at a piece of technology. We're actually stepping into a specific room at a very specific time.
To witness a very specific domestic argument.
Yeah, exactly. I want you to set your internal clock to March 1985. It is a Tuesday evening. It's raining, because it's always raining in 1985 England, and you have just come home from school or work.
And you are mentally vibrating.
You are. You've spent the entire day thinking about a few lines of basic code you need to fix, or maybe you are just itching to load up Elite and trade some grain. You walk into the living room, cassette tape in hand, ready to claim your digital destiny. But there is this massive, immovable object in your way.
The rest of the family.
The family.
Yeah.
And they're settled. They have the tea and biscuits out. Coronation Street is on in 5 minutes, or maybe the A-Team is about to start.
Yeah.
And the real tragedy of your existence is that your gateway to the future, your ZX Spectrum or your Commodore 64, is physically tethered to the only color screen in the house.
The family television receiver. You know, this is the era of the domestic compromise. It is a period in computing history defined not just by what the hardware could do, but by the actual friction it caused in the living room. We call this the turf war.
The turf war. I love that term. And that is exactly what we are unpacking today. We're looking at a pivotal moment in tech history where the home computer essentially tried to file for divorce from the television set. We are diving into an article from Personal Computer World, March 1985.
Written by Gareth Jefferson.
Right, by Gareth Jefferson. It's titled simply RGB Monitors. But don't let that dry title fool you. This isn't just about specs. This is a story about a battle for visual clarity, the limitations of physics, and the sheer eye-watering expense of trying to upgrade your view.
It really is a fascinating document because it captures a transition point. We are moving from the fuzzy TV era where everything was a bit blurry and vibrating to the era of the dedicated monitor. But as we're going to see, it wasn't a clean break. It was messy, it was expensive, and technically very complicated.
So our mission today is to answer a few questions that I think anyone who lived through the 80s has asked themselves at some point. Like, why did early computer graphics look so terrible on a normal TV? Why did the text vibrate? What on earth is the 8-color ceiling? And finally, we're going to referee a hardware shootout between 3 specific televisions-cum-monitors from 1985.
To see if spending the equivalent of nearly £1,000 in today's money was actually worth it.
Yeah, it's a steep price to pay for clarity.
It is huge.
But before we get to the price tags and the soldering irons, we have to understand the core problem. Why was the picture so bad to begin with? I think most of us remember the drifting dots and the color bleed, but I never really understood why it happened. Why couldn't I just plug my computer into the TV and get a perfect picture?
To understand the why, we really have to follow the journey of the video signal, and it is a surprisingly long, tortuous, and inefficient journey. Gareth Jefferson does a great job in the source material of breaking this down, starting right at the source, which is the camera.
Okay, let's trace it. Because in my head, a video signal is just a picture sent down a wire. But it's more complex than that.
Much more. Let's start with a professional color TV camera in a studio. Inside that camera, you don't just have one sensor. You effectively have 3 monochrome cameras working in unison. One filters for red light, one for green light, and one for blue light. So right out of the gate, before the signal even leaves the camera, you have 3 separate distinct video signals, R, J, and B.
Look, the timing right. The computer or camera needs to tell the screen when to start a new line or a new frame.
Correct. Those are the synchronization pulses. Horizontal sync, which says start a new line, and vertical sync, which says start a new frame. So in a pure, unadulterated system, what we call the gold standard, you are juggling 5 distinct signals. Red, green, blue, H-sync, and V-sync.
That sounds like a lot of wires.
Yeah.
If I look at the back of a modern TV or even an old one, I don't usually see 5 separate plugs for one picture.
And that's the problem. In the world of 1950s and 60s, broadcast television bandwidth was precious. You couldn't transmit 5 separate signals over the airwaves to an antenna on a roof. It takes up too much electromagnetic space, so the engineers came up with a solution called composite video.
Which implies composing them, like smashed together.
Precisely. They take those 5 beautiful, distinct signals and crush them into a single voltage wire. They mix the color data, the chrominance, with the brightness data, the luminance, and they bury the sync pulses in there too.
I want to use an analogy here because this seems crazy to me. It's like, imagine you have a gourmet meal. You have steak, some peas, and some mashed potatoes. Distinct flavors, distinct textures. That's your RGB.
Right.
Composite video is like taking that meal, throwing it into a blender, hitting puree, and turning it into a brown sludge. And then you pump that sludge through a pipe the gable to the TV.
And here is the kicker. The TV's job is to take that sludge and try to unblend it. It has to look at the brown mush and say, okay, I think this bit was a pea and this bit was the steak.
Which is impossible to do perfectly.
It is physically impossible to do perfectly. The TV uses filters to guess which frequencies are color and which are brightness, but it makes mistakes. That is composite video. But for home computers, it got even worse.
Worse than the sludge.
Much worse.
Yeah.
Because most TVs in 1985 didn't even have a composite video input. They just had that one little silver socket on the back, the aerial socket.
Well, the RF socket.
This is where the RF modulation nightmare begins. You see, the computer, let's say your BBC Micro, generates a pristine digital signal internally. It knows exactly which pixel is red and which is blue. It has the gourmet meal ready to go.
But it has to get it into the TV.
And the TV only understands broadcast signals, so the computer has to lie. It takes that digital info, converts it to the composite sludge, and then, and this is the heartbreaking part, it modulates it onto a high-frequency radio wave.
It's pretending to be a TV station.
Exactly. It mimics a broadcast signal like BBC One or Channel 4. It sends that through a cheap coaxial cable into the TV. The TV then thinks it's receiving a broadcast from a transmitter miles away, so it sends it through a tuner, demodulates it back to composite, and then separates the colors.
So let me get this straight. We are encoding digital to analog, then modulating analog to radio frequency, then demodulating radio frequency back to analog, and then decoding analog back to color.
It's a game of telephone, but with electrons, and every single step adds noise.
Jefferson mentions the irritating drifting dot effect. That was the absolute bane of my existence. What exactly causes that?
That is a direct result of the unblending failure. In a composite signal, the color information is encoded as a high-frequency wave, but fine detail like the sharp edge of a text character is also a high-frequency signal. The TV gets confused. It looks at the sharp edge of a letter A and thinks, is this a sharp white line or is this a burst of color?
And it gets us wrong.
It guesses wrong. It interprets the sharp edge as color data, so you get these shimmering rainbow-colored dots crawling up the side of your text. That's cross-color interference.
And for a moving picture like the A-Team blowing up a Jeep, nobody notices because the explosion is chaotic anyway.
Exactly. The human eye is very forgiving of motion. Television was designed for moving faces and explosions. But computer text is static. It has sharp, high-contrast edges. That is the worst-case scenario for RF modulation. That's why your code looked like it was vibrating.
So the premise of this article and the mission of this deep dive is escaping this loop, bypassing the tuner entirely.
Right. We need to stop the game of telephone. There are two ways out. The first is direct video or composite input. That bypasses the RF modulation and demodulation. It's better. It's like drinking the smoothie directly without shipping it across the country first, but the ingredients are still mixed.
And the gold standard is RGB.
Red, green, blue. Connecting the computer's brain directly to the electron guns in the TV tube. The monitor doesn't have to guess. The computer says, fire the red gun, and the monitor fires the red gun. Minimal degradation.
It sounds perfect. It sounds like the solution to all our problems. But as with everything in tech, there is a catch. And this leads us to the second part of our discussion, the 8-color ceiling.
Yes. This is a concept that confuses people even today when looking back. We think RGB means millions of colors. If you buy an RGB monitor today, it displays 16 million colors. But in 1985, for most home computers, RGB meant exactly 8 colors.
And this isn't a limitation of the screen rate. This is a limitation of the signal type. The article draws a clear distinction between analog RGB and TTL RGB. We need to really break this down because TTL sounds like terrifying jargon.
It does, but it's actually quite simple. Let's start with analog. Broadcast monitors, the really expensive stuff used in TV studios, like the Sony Profile mentioned in the text, use analog RGB.
And analog means infinite variation.
Think of it like a dimmer switch on your wall. You can turn the light fully on, fully off, or anywhere in between. You can have it at 50% brightness, 10% brightness, or 99% brightness. In an analog signal, the voltage represents that brightness. 1 volt is full on, 0 volts is off, 0.5 volt is gray.
So you can mix a little bit of red, a lot of green, and a medium amount of blue to get, I don't know, a nice terracotta.
Exactly, infinite shades. But computers in the early 80s didn't think in analog. They thought in binary. They used TTL, transistor logic.
And in the TTL world, there are no dimmer switches.
No dimmers, only light switches. A signal is either 5 volts, which is high or on, or it's 0 volts, which is low or off. There is no half on.
So let's do the math on that. I want you to visualize this. You have 3 spotlights pointing at a wall, a red one, a green one, and a blue one. and you have a simple switch for each.
Right, 3 switches. Each switch has 2 positions, on or off. That's 2 times 2 times 2. 2 cubed. That equals 8. That is the hard mathematical ceiling. You physically cannot produce more than 8 colors using simple TTL RGB.
I think we should list them. I want to list them because it really paints the aesthetic of the 1980s. When you look at old Spectrum or BBC micro games, they have a very specific look. It's because of this exact list.
It is the palette of our childhoods. Let's run through the combinations. 1 is red switch only, you get red.
Makes sense.
2 is green switch only, you get green. 3 is blue switch only, you get blue.
Blue primary.
Then 4 is red plus green, you get yellow. 5 is red plus blue, you get magenta. 6 is green plus blue, you get cyan.
Can be extreme.
7 is all 3 on, you get white. And 8 is all 3 off, you get black.
And that's it.
That is the entire universe of color.
Notice what is missing from that list. No orange, no brown, and most devastatingly, no gray.
No gray is the big one. In a modern interface, we use gray all the time for shadows, for borders, for softening the eyes. In 1985, TTL RGB, you either have full blast, blinding white, or total darkness.
That explains why old word processors were so aggressive on the eyes. It was white text on a blue background or bright green on pitch black. There was no subtlety. It's a very vivid primary harshness, as the source implies.
It's a digital shouting match. Every pixel is screaming its color at maximum volume.
Now, I know there were workarounds. The IBM PC had CGA, which famously had those terrible palettes, but it technically had 16 colors. How did they cheat the math?
They added a 4th switch, a 4th wire. They called it the intensity signal. So you have RGB and I.
So does that actually work?
If the intensity switch is on white, it boosts the brightness of all the active guns. So if you have red turned on and intensity turned on, you get bright red. If you have red turned on and intensity off, you get dark red.
So 8 times 2 is 16.
Exactly. But the monitors we are looking at today, these hybrid TVs, were primarily designed for the strict 8-color standard. In fact, Jefferson points out a really interesting compatibility issue. If you plug a TTL computer, which outputs 5 volts, into a pure analog monitor, which expects a maximum of 1 volt, what happens?
You blow it up.
You might, but usually the monitor just clamps the signal, it sees the massive 5-volt spike and treats it as full-on. It doesn't know how to do anything in between. So even if you have a fancy analog screen, if the computer is TTL, you are still stuck with the 8 crayons.
So we have solved the fuzziness.
Yeah.
We have sharp pixels, but we are stuck with a box of 8 crayons.
Precisely. But there is another problem, and this one might be the biggest heartbreak for the serious business user in 1985. You spent the money, you've got the RGB cable, and you think, finally, I can do professional word processing.
Ah, the 80-column mirage.
The dream of 80 columns.
For the listeners who might not know, standard TV modes back then were usually 40 columns, 40 characters across the screen. That's like reading a large print book. But professional documents, typewriters, business letters, they were all 80 columns wide.
If you wanted to do spreadsheets or write a serious report, you needed 80 columns. But the article drops a hard truth. Ordinary televisions are simply not capable of adequately displaying 80 characters on a line, even these new hybrid ones with RGB inputs.
But wait, if we have bypassed the RF modulation and we have sharp pixels, why can't the TV show the letters? We just established that RGB is the gold standard.
It comes down to the physical construction of the tube itself. We have to talk about the shadow mask.
Okay, I've heard this term thrown around for years. Shadow mask. It sounds mysterious. What actually is it?
To really get this, you have to visualize the architecture of a pixel. In 1985, a pixel on a screen wasn't a single glowing square like on your phone today. The screen was covered in triads, clusters of 3 dots, red phosphor, green phosphor, blue phosphor.
Painted on the glass.
Painted on the inside of the glass. Now, behind that glass, inside the vacuum tube, there is a metal sheet with millions of tiny holes in it. That is the shadow mask.
It's a colander.
It is exactly a colander. Its job is to act as a stencil. When the red electron gun fires, the beam goes through the holes and hits only the red phosphor dots. The mask blocks it from hitting the green or blue ones.
So the holes determine the resolution.
Exactly. The spacing of those holes, the dot pitch, determines the finest detail you can draw. Domestic TVs, even the nice ones, were designed to show moving faces. A face doesn't have hard edges, so to keep costs down and brightness up, TVs had a coarse shadow mask. The holes were relatively far apart, maybe 0.6 millimeters or more.
And here's the problem. If the computer tries to draw a tiny letter E in 80-column mode,
that letter might only be 0.3 millimeters wide on the glass.
so the letter is smaller than the holes in the colander.
Exactly. The math physically doesn't work. The letter falls between the holes or spans across two holes in a messy way. The TV physically cannot resolve the detail. It doesn't matter how sharp the signal is coming from the computer. If the screen's pixels, the phosphor triads, are bigger than the computer's pixels, it's gonna look like a blur.
It's like trying to make a mosaic out of dinner plates instead of tiny tiles. You just can't get the detail.
That's a great analogy. So Jefferson's verdict is brutal. Any attempt to display 80 columns will still result in blurred, unreadable characters. If you want 80 columns, you can't use a hybrid TV. You need a dedicated high-resolution monitor like the Microvitec Cub.
Which is even more expensive and couldn't be used to watch the A-Team.
Exactly. So the turf war compromise is only a partial victory. You get the TV out of the living room, you get sharp colors for games in 40 columns. But if you are a serious writer, you are still squinting.
Speaking of getting the TV out of the living room, let's move to the main event, the hardware shootout. Gareth Jefferson reviews 3 specific units in this article. These are televisions cum monitors.
Which is a very clumsy phrase for a TV with extra sockets.
It really is. And we have 3 contenders, the Fidelity CTM-1400, the Ferguson MC01, and the Hitachi CPT-1444. And before we dive into the actual specs, we have to address the elephant in the room, the price.
The prices are eye-watering when you adjust for inflation.
So the Fidelity and Ferguson were both priced at £229 in 1985. Now, I ran this through the Bank of England inflation calculator, and with a multiplier of roughly 3.93, that is nearly £900 in 2026 money.
£900 for a 14-inch screen.
To put that in perspective, what could you buy for £229 in 1985?
That was the price of a decent secondhand car. You could buy a Ford Cortina that ran for that money. You could take a family of 4 on a holiday to Spain.
So you are walking into the electronics shop, and you are choosing between a vehicle that transports your family and a small box that lets you play Manic Miner without the dots shimmering.
That is a massive statement of priority. It shows just how desperate people were to escape the fuzzy TV era. This wasn't an impulse buy. This was a major household investment.
Which is why the review focuses so heavily on versatility. If you're spending £900, this thing better do everything. It better be a TV, a monitor, a VCR display, and make tea in the morning.
Let's look at how they stacked up.
Contender number 1, the Fidelity CTM 1400. This one seems to be the forward thinker of the group.
It is. The Fidelity stands out because it adopted a standard that was brand new at the time but would become legendary in Europe. The SCART connector.
The Euro connector, the big rectangular block with the slanted corner.
Yes. The 21-pin beast. In 1985, this was cutting edge. The idea was brilliant. One plug to rule them all. It carried composite in, composite out stereo, audio RGB, analog, and switching signals. It was the Swiss Army knife of cables.
And the review praises this. It says ready-made leads are available for popular micros. That is a huge plus. You don't have to be an electrical engineer to plug it in.
Right. And technically, the Fidelity does something very clever. Since it expects analog RGB at 0.7 volts, but computers output TTL at 5 volts, the leads incorporate resistors to drop the voltage down. It's a simple, elegant solution.
But it's not perfect. The review mentions a flaw with compound sync. Here we go with the sync again. Why is this always the stumbling block?
Because there was no standard. Some computers, like the BBC Micro Output, separate sync signals. One wire for horizontal, one for vertical. SCART, by design, usually expects compound sync. That's everything mixed together on one pin.
So if you have an IBM PC or a machine with separate syncs,
the Fidelity might just stare at you blankly. Or you might have to wire the sync signal into the composite video pin, which is messy. It's a reminder that standard in 1985 didn't really mean standard, it meant standard-ish.
There's a note about the user experience. Manual TV tuning is fiddly.
A classic 80s complaint. No digital scanning. You had to turn a little thumb wheel or a plastic screw until the picture stopped rolling. For £900, you'd hope for a button.
Okay, moving on to contender number 2, the Ferguson MC01. Same price, £229. But the connector situation here is bizarre.
Weird is the polite word. Ferguson decided to ignore SCART and use DIN sockets. A 7-pin DIN for RGB and a 5-pin DIN for composite.
Now, were these standard DIN layouts? Like, could I go to a shop and buy a 7-pin DIN RGB cable off the shelf?
Gareth Jefferson explicitly says neither of these is standard. It's proprietary madness. It's the Apple Lightning connector of 1985.
This is the proprietary trap. You buy the monitor and suddenly you're hunting for a very specific cable that only works for this one screen.
And at the time of review, only a BBC micro lead was available. If you had a Commodore or a Spectrum, you might be out of luck until Ferguson decided to release more leads. You effectively have a 900-pound paperweight.
However, the performance was good.
Yes, clear improvement over RF. And it had a nice feature regarding sync. It accepted separate sync inputs, but they had to be negative going.
Negative going sync. I feel like we are getting into deep tech here, but what does that mean simply?
It's just the polarity of the pulse. Does the voltage jump UP to say new line, which is positive, or drop down N to say new line, which is negative? Most computers use negative, so the Ferguson was actually quite compatible with the logic, even if the plug was a nightmare.
Now we get to the third contender. And I feel like we need dramatic music for this one. The Hitachi CPT-1444.
The budget option.
Budget at 210 pounds. That's still over 800 pounds today. So you save about 75 quid in modern money compared to the others. But what do you give up?
You give up almost everything. First, you give up the composite input entirely.
Wait, really?
Yes, it is RF or RGB only. There is no middle ground.
That is a massive omission. If I have a VCR, I want to plug it in via the video socket for better picture.
You can't. You have to use the aerial lead just like on an old TV. So for video watchers, this is a downgrade. But the real horror story, and I mean absolute horror, is the do-it-yourself aspect.
This part of the article made my jaw drop. Tell us about the cable situation.
Okay, so you buy the Hitachi. You open the box. You find a general purpose lead. One end has a D-ion plug that fits the Hitachi.
Okay, so far so good.
The other end has nothing.
Nothing. Like a blank connector.
Just bare wires. Stripped copper.
You are joking.
I am quoting the article directly here. Soldering a suitable connector for your computer will be your responsibility.
Your responsibility? That is cold.
Imagine walking into an Apple store today buying a studio display, and the genius hands you a cable with frayed wires at one end and says, here's a soldering iron. Figure out the pinout for your MacBook yourself.
It's inconceivable.
But in 1985, this was the barrier to entry. This was the hobbyist tax. To save that 19 pounds or 75 today, you're expected to go to Maplin or Tandy, buy a 5-pin or 8-pin D-ion plug, find a wiring diagram for your computer, and physically solder the connection.
And if you get it wrong?
If you cross the red wire with the 12-volt power rail, you fry the monitor, or you fry the computer, or both.
That is high-stakes DIY. And for that reason alone, the Hitachi feels like a trap for the unwary. It's cheaper, but the sweat equity you have to put in is enormous.
It definitely is. It's for the handy user only. If you just wanted to plug and play, this machine would leave you crying in the living room with a useless cable and a burnt finger.
It does have one redeeming feature, though.
Yeah.
The contrast control.
Yes. It seems the contrast knob also adjusted the input sensitivity, so you could tweak it to work with either analog levels, which is low voltage, or TTL levels, which is high voltage. That's actually quite a clever, flexible feature. It's just a massive shame about the soldering.
So we have the Fidelity with its SCART, which feels like the winner, the Ferguson with its weird DINs, and the Hitachi with its bare wires. It really shows that there was no standard for RGB yet. It was the Wild West.
It was, and that chaos extends to the signal themselves. We touched on sync earlier, but the source dives into sync logic and cheating.
Cheating is a strong word. What were the manufacturers doing?
They were trying to survive the chaos. We mentioned that computers output 5-volt TTL, but monitors expected 1-volt analog. If you feed 5 volts into a delicate 1-volt circuit, you could damage it or at least get a washed-out, blindingly white picture.
So how did they handle it without blowing up?
A little bit of cheating in the input circuitry. They built clamping circuits. Basically, the monitor looks at the incoming voltage. If it's huge, like TTL, it clamps it down to a safe level. If it's small, like analog, it lets it through. It allowed them to market these sets as universal without having to put a big switch on the back.
It's clever engineering. But I want to circle back to the listener's perspective here. Even if they clamp the signal, they are effectively turning a loud shout into a quiet shout. They aren't turning it into a conversation.
Exactly. You are still limited by the source. If the computer is shouting on, N, or OFF, the monitor can only display on or OFF, regardless of how much you clamp the voltage. That is why the 8-color ceiling remained even on these versatile monitors.
There is another technical nuance here regarding sync. The article mentions that sync signals are almost always TTL, even on analog monitors. Why is that?
It comes down to the nature of time. Color is qualitative. It can be light red, dark red, medium red. But timing is binary. You are either at the end of a line or you aren't. You are either starting a new frame or you aren't.
There is no halfway to starting a new line.
Exactly. So sync signals remained digital TTL pulses even in the high-end analog world. It's one of the few places where the standards actually agreed.
So we've covered the tech, the cables, the soldering burns, and the massive cost.
Yeah.
Let's zoom out to the big picture, the outro, the verdict on the turf war. Do these machines solve the problem?
It's a nuanced victory. It's a yes but.
Let's do the yes first, the picture quality.
Undeniable improvement. Jefferson says it is particularly noticeable the freedom from the irritating drifting dot effect. If you were a gamer or if you did 40-column programming, moving from RF to RGB was like putting on glasses for the first time.
I remember that feeling. The first time I saw a stable image, it felt solid. It felt professional.
And socially, it was a massive win. You had your own screen, no more fighting over the A-team. You can code while the family watches TV. That peace of mind alone might be worth the 900 pounds.
But on the flip side, the no. The 80-column dream.
Dead on arrival. If you bought this hoping to turn your BBC Micro or QL into a professional workstation for spreadsheets and high-density text, you wasted your money. The shadow mask limitation, the colander effect meant you were still stuck with 40 columns. For serious work, you still needed a dedicated non-TV monitor.
So who was this for?
It was for the serious enthusiast, the person who had a VCR because these sets handled video inputs while a computer and a desire for quality, but maybe couldn't justify buying two separate screens. It was a bridge device.
The article ends with a value proposition. It says the extra cost, about 19 pounds more than a standard TV, is well worth considering.
I agree with that. If you were going to buy a small portable TV anyway, which cost around 200 pounds, spending the extra 20 to get RGB capability was a no-brainer. It future-proofed you. It opened up the world of clear computing, even if it wasn't perfect.
It represents a maturation of the hobby. We were moving away from computers as toys plugged into the telly to computers as dedicated machines requiring dedicated hardware.
It's the moment the computer demanded its own space. It demanded its own pins, its own voltage levels, and its own screen. It stopped being a parasite on the television and started being a partner.
I want to end with a thought that struck me while reading this. We spent so much money, thousands of pounds in today's money, chasing this clarity, chasing sharp pixels, trying to get rid of the fuzz.
And today?
Today we download CRT filters for our emulators. We pay good money for hardware scalers that artificially inject scan lines and shadow mask effects. We add the bleed back in.
It is ironic. In 1985, perfection was a square, solid pixel. Today, perfection is a glowing, slightly fuzzy phosphor dot. We romanticize the struggle.
Why do you think that is? Is it just nostalgia?
I think it's because that fuzz smoothed over the cracks. Modern sharp pixels expose every flaw in the pixel art. The fuzz blended the colors for us like a natural anti-aliasing. We didn't realize it at the time, but the bad TV picture was actually doing some of the artistic heavy lifting.
That is a profound thought. The sludge was actually the secret sauce.
Exactly.
Well, on that note, I think I'm going to go check if my SCART cable is fully plugged in. It feels a bit loose, and I'm pretty sure I saw a drifting dot.
Just don't bend the pins. And put the soldering iron away.
Thanks for listening to The Deep Dive. We'll catch you on the next one.